Acceleration. Let's start with average acceleration, or a to the sub x, avg. And the formula for that is where your average acceleration is your change in your velocity in your x direction divided by your change in time, which is equivalent to your final velocity in your x direction minus your initial velocity in your x direction divided by the quantity of your final time minus your initial time. The unit for this is interesting. We know that the SI unit for velocity is a meter per second, and the SI unit for time is the second. So the SI unit for average acceleration is a meter per second, or can also be written as meter per second squared. Now, acceleration is a vector quantity, which means it has both a magnitude, which tells you the strength of your acceleration with your unit in meters per second squared, and it also has a direction. So again, to repeat, a vector quantity has a magnitude and a direction. Now, when you're dealing with vector quantities, direction, of course, is important, and velocity, which is also a vector. When we're talking about direction, and we have a negative direction, we put a negative out in front of our velocity value. But what about for acceleration? Well, it turns out we can use a negative out in front of acceleration to determine direction, but a negative does not always mean negative direction. So I wanted to draw a little table here and show you what a negative A can mean and a positive A can mean. Now, if an object is moving in a negative direction, so this here is my direction, if an object is moving in a negative direction, but their velocity is increasing, or in other words, their change in velocity is positive, they will have a negative value for their acceleration. And the reverse is true, where if an object were moving in a positive direction, but they were slowing down, or their delta V were negative, they would then have a negative acceleration. So then what about positive acceleration? Well, you can have a positive acceleration if your direction is positive and the object is speeding up. Or you can have a positive acceleration if you have a negative direction and the object is slowing down. So you should memorize this table. Now, what about instantaneous acceleration, or your acceleration at some particular moment in time? Recall, to find instantaneous velocity, you will take the derivative of your position as a function of time equation. In this case, we're going to take the derivative of our velocity as a function of time. So if I have some velocity as a function of time equation, I need to then take the derivative of that, and that will give me the instantaneous acceleration. Also, this can be written as dv dt. Or, and I'll be talking more about this in a little while, it's the double derivative of a position as a function of time equation. And so that could be written as double prime as a position as a function of time, or this can be written as d squared x over dt squared. Yes, that will also give us acceleration. So I'd like to talk with you a little bit more about acceleration with a graphical representation. So I'm going to draw a velocity versus time graph. So in this velocity versus time graph, I have some function drawn in the color green. I have 2 points drawn in this function, point A and point B in blue. And one thing you can be asked to find in a velocity versus time graph is the average acceleration. And so average acceleration, which I will draw in purple, would be our straight line, the slope of our line between points A and B. So here we are, and so my acceleration, we'll say in the x direction, my average acceleration will be my change in velocity over my change in time, or that will be my velocity at position B minus my velocity at position A, divided by the time at B minus the time at A. Of course, this is also known as the slope of my purple line. But what if I wanted to find the instantaneous acceleration at, say, point B? The line tangent to point B, the slope of that line, will represent the instantaneous acceleration at point B. So let me go ahead and draw that for you. You notice my tangent to point B is quite different to my purple line. So the average and the instantaneous values here will be quite different. Now, to find this instantaneous acceleration, I would need to know the formula for the function of the green line. And then I would take the derivative of that function, and then I would plug in the time represented on the graph for point B. And we'll do an example of this in a moment. Just writing this out, my instantaneous acceleration will then be the derivative of my velocity as a function of time equation of the green curve. Now, I can also use a velocity versus time graph not just to find acceleration, but to also find displacement. Now, as you recall, velocity average, x average, is equal to your displacement over your change in time. If I could somehow multiply both sides of this equation by change in time, my change in time multiplied by my average velocity will give me my displacement. If we look at this graph a little bit closer, we can see that on the y-axis I have my velocity value, and on my horizontal axis, if you will, I have my time. So one way of looking at this is if I can multiply whatever value I'm interested in on the vertical axis multiplied by my value on the horizontal axis, or my velocity multiplied by my time, that should give me my displacement. And sure enough, that is the case. If you can find out what your function is of your green line and multiply that by your time value, your velocity multiplied by your time value, you can find out your displacement. And in essence, what that does is it gives us the area under your curve, and it's that area that actually gives us the displacement. Now, it's easy to find area of a graph if you're dealing with a rectangle or a triangle. But what if you are dealing with some sort of function like my green line? Well, then the math gets a little more interesting, and you can use something called an antiderivative or also something called an integral. I'm going to introduce this to you now, but we'll be talking more about this later. Now, if we're interested in finding the area under a particular curve, and we need to use something called an antiderivative. So we need to look at velocity here when we're using a derivative. And so my instantaneous velocity is dx over dt. Now what I want to do is go ahead and multiply both sides by dt. And what I will end up getting is v sub x dt is equal to dx. Now, to solve for this interesting looking equation, I'm going to, what we say, integrate both sides of this equation. By doing that, I'm going to draw my little integration symbol here. And then what I'm going to do is, instead of taking the derivative of these equations, I'm going to do the exact opposite of taking the derivative. So in other words, if I were to take the derivative and I would get the answer Vx, then what was it before I took the derivative? And it turns out that would come out to be V sub xt. The right side of the equation, if I took the derivative and it was just left with dx, I actually started with x. Now this would be from points, say, A to B, and so we're going to do B up here, A in the bottom, B up here, A in the bottom. And we also need to consider the fact that whenever you integrate something, you need to add a constant. So we have a constant there. Now, because we have a constant on both sides of the equation, we can go ahead and cancel those out. And see that I'm left with V sub xt, and I'm going to put this little symbol here, B at the top here, A at the bottom there, is equal to x, the symbol of B at the top, A at the bottom there. And what I'm simply going to do is plug in, on the left side of the equation, the V sub x stays there, and I'll plug in the time at B minus the time at A, and that will be equal to the position at B minus the position at A. So the right side of my equation is my displacement, or the area under the curve between points A and B. And the left side of the equation, then, we can plug in our values for time. If we started at a time of 0, then my t sub A just becomes 0, so that goes away. And I'm left with V sub x multiplied by t sub B. Gives me my displacement. Now again, we're going to be talking a lot more about antiderivatives and integration, but I thought this was a good time to introduce this to you. All right, let's talk a little bit more about graphing, and what I want to do now is look at a position versus time graph with you again. If you refer to some of my previous lessons, you should see some examples of position versus time graphs. So we have a position versus time graph, and let's say we have a line that looks just something like this. Starts at the origin, it's a straight line, and my position as a function of time is simply just t. Now, if I asked you for the velocity of this object looking at this graph, hopefully you can see that the average velocity here is going to be the slope of this line. But because the line is a straight line, it's also the instantaneous velocity. And that is also the derivative of the equation. Now, what is the derivative of the equation t, where t is your variable? Well, that is simply just 1 meter per second. And what if, instead of asking for instantaneous velocity, I asked you for instantaneous acceleration? That would be the same thing as the double derivative of my equation, or once you've taken the derivative of t, which is 1 meter per second, then you take the derivative of your 1 meter per second, and that ends up being 0. So whenever you have a straight line or a constant slope in a position versus time graph, your acceleration comes out to be 0. Okay, let's do an example. Let's say I have a velocity in the x direction as a function of time that's equal to 40 minus 5t squared. And what I want you to find, so this is my given. So what I want you to find is the average acceleration if my initial time value starts at 0 seconds and my final time value is at 2.0 seconds. The formula that we are going to use is the formula for average acceleration, which is going to be my final velocity minus my initial velocity over my final time minus my initial time. Now for solving, we're going to go ahead and start plugging in numbers. My V final is going to be 40 minus 5. The time is at 2 seconds squared. Minus my initial of 40, the quantity of 40 minus 5 multiplied by 0 seconds squared. This is going to all be over a change in time of 2 seconds. So my average acceleration is going to be 40 minus 20 minus 40 all over 2. And that is going to give me a negative 10 meters per second squared. Now, if my graph of this function looks something like this graph I have here, what I want to figure out is what does this negative in front of this 10 meters per second squared mean? It either means the object is slowing down, or it means the object is speeding up in the negative direction. And so this is all happening at 2 seconds. So at 2 seconds, I'm going to find out where that is on the graph. Here's 2 seconds. And I'm going to come up to where my red line meets my green line. And I'm going to come over to the vertical axis here where velocity is. And what I want to look at is say, is this a positive value or not? And this right here is a positive value. That positive value means that the object has a positive velocity at 2 seconds, and they are therefore moving in a positive direction. And so since they are moving in a positive direction, this negative in front of my negative 10 indicates slowing down. Or we could say the object is decelerating. Going back to our original function, I'd like to now find the instantaneous acceleration, or a sub x, when t is at 2 seconds, at a time of 2 seconds. So the formula that we are going to use here is we are going to take the derivative of our original function, which is simply going to be negative 10t. And so for solving then my instantaneous acceleration, which is the derivative of my velocity of a function of time, I'm going to plug in 2 seconds for t, and I'm going to get a negative 20 meters per second, or meters per second squared. Now in this case, this is still happening at 2 seconds. And since this is happening at 2 seconds, we can say that this is positive, and therefore the negative means the object is slowing down. Here's your practice. Thanks for watching.